Hello, ENET 140. This is the second recorded lecture for our op-amps Fiori textbook, Chapter 5, on the practical limits of real op-amps in negative feedback circuits. This is Bellingham Technical College, winter quarter 2020. So when we left off with lecture 1, we had covered gain bandwidth and slew rate, which are frequency-dependent characteristics of real op-amps. And now we're going to dive into offsets, which are very much a DC characteristic, although they will of course affect AC signals by producing a DC offset that signal, AC amplified signal, would ride on, which in this case we didn't want. So what is an offset? It's an undesirable DC offset to an AC input signal, or I could add to a DC input signal, in which case it tends to have even bigger consequences due to component asymmetry, especially in the differential amplifier. That was something we touched on way back in Chapter 1, how at least to achieve a good common mode rejection ratio, the two parts of a diff amp had to be exactly the same. And I believe in the first lab we went over measuring things like our input offset currents and our output offset voltages, getting an idea of what that symmetry was and what its consequences were on our voltage output, which is what we care about from an amplifier. It's the output voltage. That's why we're amplifying it in the first place. We want a bigger output. So here we're going to walk through how some of the things that we measured in that first lab are actually listed in the datasheet. So we can use them as design inputs without having to necessarily use an ammeter or measure current with a calibrated resistor with our scope, and get an idea of how we would design around what we know is not going to be an ideality in the circuit. Because let's face it, the manufacturers have tested this. They have an idea of what the range of quality control is, and therefore what the range of symmetry of the diff amp portion of various amplifiers is, and so they capture a lot of that in the spec sheet. So this will give us an idea of how to take those listed input offset non-idealities that you can see in your spec sheet and how to translate that into, and how bad is my output voltage signal going to be? Okay, so one of the things we have to remember in using this is the DC biasing differences, which includes any of our input offsets, voltage or current. They get amplified as they go through the amplifier, and they get added to our amplified AC signal or an amplified DC signal. And we won't get into this in this section, but just as a reminder, we of course use different biasing methods for a field effect versus a bipolar junction transistor. And so the sources of the differences, the asymmetries in the diff amp section are going to be different. In the case of the BJT, you might get non-idealities and asymmetry due to betas being different from one side of the diff amp to the other. Whereas if you're using FETs to make up your diff amp portion of your op amp, the main culprit in your asymmetry is probably transconductance differences one to the other side. Either way, you're going to get something. Okay, so in an ideal op amp, no current's going to flow into the input terminals. But in a real op amp, you're required to have a very small amount of current flowing into the inverting and non-inverting inputs. And by very small, this is negligible, and that's why we were able to assume infinite input impedance. But in reality, there'll be some, and we will use that very small amount to create a circuit model that we'll use to evaluate these non-ideal offset currents and voltages that we can find in the spec sheet. So input offset current. Back in the lab we found that these were the different currents that were being drawn by the different sides of the diff amp, and we can assume that one of them listed as IB negative, and that's IB inverting, is flowing into the inverting terminal, and IB plus, IB non-inverting, is flowing into the non-inverting terminal. So we are admitting now that we have a very small amount of current flowing into those two terminals. If we subtract IB inverting from IB non-inverting and take the absolute value, we define a characteristic called the input offset current, or I sub OS, or I sub IO, input offset. This is specified by the manufacturer and it's cited in the spec sheets. You will often get a citing value for IB, and it will usually not distinguish whether it's inverting or non-inverting. It'll just be IB, and it'll be usually much bigger than your IOS. And we'll go through how you use either one to using a circuit model, how you deploy either one to figure out what the impact's going to be on your voltage output. Okay, in an ideal op-amp, we have the same voltage at the inverting and non-inverting inputs. We use that to create the virtual ground, do a lot of our circuit analysis. Real amps, op-amps, obviously, if you have some current flowing in, you're going to get a real voltage difference between the two. Again, very, very small, but we'll define it now. So again, the IB inverting and non-inverting represented the actual real tiny amount of current flowing into each of those terminals, and the IOS was the difference between those tiny amounts of current expressed as an absolute value. Well, that tiny amount of current ends up resulting in a tiny voltage difference between the inverting and non-inverting terminals. Okay, that's going to be a spec sheet value called VOS, V subscript OS or OI. So that's input offset voltage. What's the actual real voltage difference that you can support between the inverting and non-inverting terminals? This has a particular definition, and it's related to your input currents and the asymmetry of the circuit, and it's the voltage difference between the inputs that you would need to impose in order to remove the DC offset at the output. So if you wanted to get rid of all of the DC offset that's due to your op-amp non-ideality, VOS is what you would have to apply if all other things were idealized. So both the input offset currents and the input offset voltage, you can think of all three of those, IB inverting, IB non-inverting, and IOS, as being sources of non-ideality on the input that can give you an offset, a DC offset at your output. So you can think of them in terms of three different input error sources. And in order to kind of wrangle those into a resultant output offset error, which is what we care about, we're going to use the circuit model. Yay! We use that to do everything, right? So here's an idealized circuit model that is used to analyze the effect of these differential non-idealities, these asymmetries. This isn't necessarily exactly how you will have your circuit configured, but just about any type of op-amp can usually be equated to some variation of these by just zeroing out or adding different resistors. So we've kind of got, non-inverting and inverting negative feedback configurations kind of all taken care of here. This is sort of like a one-size-fits-all model circuit. So we're going to assume, here's our negative feedback network with our RI and RF. So that's part of the feedback. We've got our op-amp, and we're going to assume that these three sources of non-ideality, these three sources of input DC offset errors, could be represented by one ideal voltage source placed here that has a value of VOS, taken right off the spec sheet. It has zero impedance, being a perfect voltage source, and it's going to sit there and pump out a voltage equal to whatever is on our spec sheet for V offset voltage. We're going to assume that we have an ideal current source feeding the inverting terminal with a current equal to IB inverting that we take right off our spec sheet. And remember, an ideal current source has infinite impedance, so it can't provide another path to ground. It just pumps current in. And we're going to assume that we have another ideal perfect current source that provides a current equal to IB non-inverting, feeding right into the non-inverting terminal. And again, it's connected to ground, but it's got an infinite input impedance, and so it doesn't provide another path to ground. So we've added IB non-inverting, IB inverting, and VOS to these positions on our hypothetical any op amp. We've added another resistor over here called R offset, which is not part of the op amp, but you could add. And we'll walk through how we might want to select the value of that to minimize the effect of IB inverting and IB non-inverting. Okay, so here's our model, and this represents any op amp. We've represented our non-idealities with voltage and current sources. So we got to get some values on these. So, and in terms of the output, because let's remember, it's the output we're measuring. We've got an amplifier because we needed to amplify a signal, so we care about what's coming on the output. We only care about the input in as much as it affects the output. So let's define a V output offset due to basically error source, symmetry error source number 1, which we're going to say, well, say number 1 is the VOS. So how does VOS affect the output? Okay, well, it's a voltage source that's only being applied to one terminal, so it's creating a differential voltage, so we could probably multiply it by a gain. And in this case, just like was the case when we were doing those gain bandwidth calculations, we use the noise gain, not just the stage gain. So remember, it's the same as a non-inverting feedback network. And given that we're putting this into the non-inverting terminal, it makes sense. Okay, so just like we did with gain bandwidth. So we can define a V out due to V in offset of A noise times the V in offset. So this is great. We can get A noise from our inverting and our feedback, just like we did back with gain bandwidth. It's equal to 1 plus RF over RI. And VOS we read off the spec sheet. Okay, so we know we're going to have an offset output error at least as big as A noise times VOS, and we can calculate that in one step. Easy algebra. But we got two more, so we got to make sure those aren't way bigger. So we're going to define the error, the V output offset, so the DC error in the output due to this non-inverting current source. Okay, well, where does this go? How does it create an error? So the current, we can say, flows from IB non-inverting. It goes through the voltage source, because the voltage source is a short. Basically, it creates voltage, but it has zero impedance. That's the characteristic of an ideal voltage source. It goes through this resistor to ground. So this current source will create a voltage source at the non-inverting terminal by KVL. So we can say, we go from ground, we have a current equal to IB plus, this is a dead short, we create a voltage equal to R offset. That voltage, because this is a short, is seen here. Okay, so just like was the case with VOS, what does an op amp do when it sees the voltage at only one terminal? It's seeing a differential voltage. It's going to amplify it, and we'll use the A noise again, just like we did with VOS. So we're creating a voltage change due to a current because we have a resistor here. Okay, so here's our second component, and just as I'm sure you guys are predicting this, the total V out offset is going to be, of course, the sum of these superposition holds. So we're just going to add them all up. Each one of these errors is additive. So we got 1, we got 2. So now we only got one more to consider. We've got this ideal current source feeding into the inverting terminal. And again, these are representations of asymmetry errors that we're representing by ideal current sources. It's a good model. This is a modeled way of accounting for our error. So we've got current we could say that there's a virtual ground. Even though we're backing off of ideality, we can still say we've got pretty much a virtual ground at the inverting terminal. So we know that this current is going to end up flowing to the output through the feedback resistor. So it's going to act pretty much the same way that a signal current would act going to the virtual ground and on through. So we know that the gain or the voltage signal at the output due to this current flow is going to be the result of the voltage drop over RF due to this point here being a virtual ground. And again, ground having come from here through the short, not from here, because this is effectively an open from a DC standpoint. Okay, so that's output DC offset error source number 3 coming from this ideal current source, representing our current non-ideal current going into the inverting terminal. So that's going to be negative current source going into the inverting terminal times RF. So our total output offset voltage error is going to be V offset 1 due to the input VOS, which we can read off our spec sheet, V output offset 2, which is due to IB non-inverting times A noise. And IB non-inverting again is off our spec sheet. We got A noise multiplying here too. And then we have V out offset 3, which is our inverting IB, and again IB again coming from the spec sheet, just times our feedback resistor, which we'll know if we set up the circuit. So we can write them all together. V out offset total is V out offset 1, which is VOS times A noise, which is also equal to 1 plus RF over RI, so that's another way of writing A noise, plus V out offset 2, which is our IB plus, and this value will come from a spec sheet. This we can set. We can choose that. So that's up to us. And here's our A noise again. And then V out offset 3, third component, is going to be negative IB inverting times our feedback resistor. So we can rearrange these things to make it easier to use the datasheet listings, remembering that IOS, and quite often we will see an IOS value on a datasheet. Remember, that's the absolute value of IB plus minus IB negative. So we can rearrange terms in this summation to make it easier to identify this in terms of IB plus and IB minus, and we end up with this entire expression. So we basically just looked at, we've rewritten this summation, and we're just looking at the components of the V out offset that are due to our IB inverting and non-inverting. So components 2 and 3. So we've just rearranged some terms here, pulled out an RF, and if we're going to relate back to IOS, this whole thing would end up as an absolute value. So it can only be positive. And yeah, and that kind of is in this, for our purposes, that absolute value will not be in our favor, because what that means is any kind of DC offset error that shows up at our output coming from the current sources can only add to the error that's coming from our VOS. So errors can't subtract from one another other than within this term. So the IB errors can only add to the VOS errors. Okay, but we can at least get rid of the IB errors. So you can see that this term in here, this V out offset 2 and 3, which come from our IB terms, these do have a negative sign. And that's what your R offset is for. If you know what this number is from a spec sheet, this number is, you know what feedback resistors you chose, you can choose a value for this that makes this entire term cancel out or be minimized. And by definition, the minimum value that this term can assume, it can't really go all the way to 0, even though we can mathematically make it 0. We define the IOS as the value that this term assumes when you've optimized R offset. So like I said, you could set an R offset that makes this term disappear mathematically just from algebra, but there are other things that we're not including in this model. So what we do is we say that if R offset is set as well as possible, such that we're minimizing this set of two terms as well as we can, we just replace this whole set of terms with RF times IOS, which is much, much smaller than I sub B. So we still gain ground in minimizing our total offset error. So in that case, if we've set our R offset optimally, we just end up with the V out offset component 1, which is coming from our VOS times the A noise, plus IOS times RF. So we'll be using either this entire expression, where this term and this term are combined in an absolute value and can only add to this term. And that would be a case of, say, R offset was not ideal or was 0. Or we'll use this expression for cases in which we've set our R offset to be ideal, and then this term here will always be smaller than the combined terms of just your IB plus and minus. So let's do an example, kind of put some numbers to this. So we got an op amp. It's a 5534. Don't know what that is, but it has an input current error. In this case, the inverting and non-inverting, the IB plus and the IB minus, are pretty much the same, and they're each 800 nanoamps. So we can have, in reality, we can have 800 nanoamps going into each of these terminals, and we have a VOS of half a millivolt. So to take care of any kind of non-idealities in the output, we would have to apply a half a millivolt between the inverting and non-inverting terminals to kind of zero the op amp. And in this case, someone has set the circuit up so that our R offset starts out at 0. And here's our feedback resistor and our inverting terminal resistor. And somebody wants to know, in this current state with no offset resistor, how much is our output offset voltage? So our offset 0, so we have to use that full expression here. We got to calculate this, we got to calculate this, although with that being 0, that's going to end up being 0. We'll end up with this term. That negative sign will flip to a positive because it's in an absolute value, and it'll add to that one. And so that's shown here with some numbers in. So we have VOS times our noise gain, which is RF over RI plus 1. So that turns out to be 11. And then we have, within the absolute value bars, we have our two current terms. So one is IB times A noise times R offset, which is 0. So this whole term will go to 0. Then we have IB times RF. It's negative. This goes to 0. You have absolute values, so this negative goes to positive. So we end up with half of a millivolt times 11, which gives us 0.0055 volts. And then this term ends up as 0.008 volts. So we have 0.0135 or 13.5 millivolts of output offset error. So that's effectively the plus or minus DC offset that we would have to add or subtract, because we don't know what it's going to be. We don't know what the sign of it is necessarily coming out. So that's, you can think of putting an error bar around an output signal. we have a 13.5 millivolt error bar around our output signal. And that's bad news if we're trying to measure something. So we want to bring that down. So let's assume that our offset is set ideally. And the ideal R offset would be a resistor value here that set these two equal to one another. So if we were going to select our offset resistor, we'd select a value of 909 ohms, and that would allow us to use our VOS plus IOS times RF, and that would lower our offset output voltage error from 13.5 to 5.6. So that's much reduced. So we've cut it in about half by using our offset resistor. So that's a powerful adjustment that we can use for these. So we've got one more example that really cinches the idea of how this relates to error. This is Fiori example 5.10. And in this case we have a 3 millivolt input signal. This is very tiny. It's a DC signal. This is the kind of thing you would see coming in off of maybe a strain gauge or some kind of resistive temperature device, or it's probably bigger than what you'd see from a thermocouple. So a lot of very critical, ordinary, everyday measurement methods will produce signals in this range. So that's definitely par for the course for DC instrument signals, which you'll need all the time. And so that's coming in on the inverting terminal. We don't see anything like an offset resistor, so we'll have to assume that it's not there. And somebody wants to know if I'm using a 411 op amp and I have these values for 20 kilo ohm feedback resistor and a 5 kilo ohm inverting input resistor, what's the uncertainty in my output? You know, what are the plus or minuses on my output signal? And that might be important to know if maybe I can distinguish it from a different output. What can I really see? So those of you who are taking statistics or who will go to work in any kind of process control studies in an internship, you'll definitely run across this kind of consideration. What can you detect? These are setting limits of detectability. So another way of stating output uncertainty is the output offset total, right? Because that offset error could go in the positive or the negative, and it's going to be an output that is unrelated to our signal. So it's gonna flank it. So I'll calculate that. So I can look up the characteristics of the 411 op amp. Our Fiori textbook lists those, and you can look up a typical data sheet. So I have an IB of 50 picoamps, an IOS of 25 picoamps, and a VOS of 0.8 millivolts. Now this is bigger than the previous one, and these other two look to be a bit smaller. Okay, if I have no offset resistor, the V output offset is going to follow this formula, which is the whole one with that middle term being zeroed, but this term probably being a bit bigger. And when I calculate R noise with my feedback resistors and I drop in my R feedback, I get a V output offset of about 4 millivolts. Okay, so no R offset there. So if I say, well, 4 millivolts seems like a lot, but what was I expecting to get on an amplified signal? Okay, well, hey, I can calculate what kind of amplified signal I'd get. It's going to be negative RF over RI for an inverting voltage amplifier. So that's 20 divided by 5, that's 4. And it'll flip the sign. So I'm only expecting a 12 millivolt output. I have a 4 millivolt error. So my actual output, and this should be a negative 12 because this is inverting. So my expected signal in an ideal world would be negative 12 millivolts, but because I have this 4 millivolt output offset error, I might measure anywhere between negative 8 millivolts and negative 16 millivolts. So that's my plus or minus 4 millivolt error band over my expected signal. That's a 33% error. That is huge. That means if I get a signal whose output is 10 millivolts, I can't tell that it's different than 12. And that might be very critical in deciding whether or not a process is acceptable based on the fact that this is a signal that I'm reading. I am going to march on here because we're getting reasonably close. I've got 3 more pages of notes to hit the related topics. But if this hasn't scared you, it gets worse. The DC offsets are themselves temperature dependent. So once you characterize your maximum error or output uncertainty due to your VOS and your IOS, or your IB if you're not using an appropriately selected offset resistor, these values themselves can change with temperature, definitely with high temperature, and that's what's known as drift. So drift basically is a second voltage signal that we add to our offset output voltage that just represents how these two change with temperature. And lucky for us, at least those temperature dependencies are usually listed as single values, so they're like a slope of each of these with respect to temperature. These are datasheet values, so we'll get those on a datasheet, plus the reference temperature about which they're taken. So we can combine these in a little formula that represents the single voltage signal that is simply due to, on the output, because that's what we care about, right? Just the output, that's just due to the temperature variation versus our reference temperature in VOS and IOS. So we're looking at the temperature variation in an error signal. Does it get worse? Does it get better? And not surprisingly, most of the time it gets worse. So just to give a quick run through on how you'd use this, going back to our same 5534 op amp, we're told it has a reference temperature of 25 degrees C. In this case, the op amp was nulled at that temperature. You'll see that in our Fiori example 511. So we take that to be the reference temperature. Somebody wants to know what's going to be our output offset at 80 degrees C. So since we nulled it at 25, the output offset was 0. So any output offset that we measure at 80 degrees C is simply due to the drift. So we don't have to go back through our formula for output offset error as a function of VOS and IOS, because in this case the problem will tell you we got rid of that at the reference temperature. So now we just have to look at the effect of temperature change, and that's what the V drift is giving us. So we plug into our V drift formula using a noise and RF. Because the V drift is an input signal, we amplify it as we go through the amplifier. Darn it, we're amplifying all these errors, which is not good, but it is what it is. We just have to keep track of it so we know our error. So we take this from the spec sheet. We were given that at 5 microvolts per degree C. And then our delta T, our A noise. We have our delta IOS per delta T, which we're given as 200 picoamps per degree C. We plug that in here. Picoamps is 10 to the minus 12. Here's our delta T and our feedback. And we get a drift voltage of 3 millivolts. So we can null out the effect, this horrible effect of our offset voltage. There are ways to do that, and I haven't hit it in the notes, but Fiori does discuss using a null potentiometer to get rid of that. But if you do and you change temperature, you'll have this V drift that is due to the fact that your VOS and your IOS change with temperature, and now your nulling is no longer going to take care of it all. And in this case, this number was reasonably similar to what we got in the first place for an output offset voltage. So very bad for small signals. Okay, Let's go to the more positive note, common mode rejection ratio. So this is going back to something we started looking at in Chapter 1, and this is a little bit more quantitative treatment on the wonderful things your differential amplifier stage do for you. And in this case, it's getting rid of noise signals. So to recap, in an ideal op-amp with a perfectly symmetric differential amplifier stage, equal signals are applied to both inputs and they're eliminated. They subtract out, and that's called common mode rejection. If the differential amplifier isn't symmetric, then common mode signals aren't completely eliminated. They're mostly eliminated, but the extent to which we get rid of them is important because we're really relying on this effect for our high gain op amps and multi-stage op amps to not be amplifying noise along with signal, because signal to noise is what we care about. The common mode rejection ratio is defined as the extent to which common mode signals are attenuated. So how much do we get rid of them? Because it's the differential signal that we want. It's our information signal that we're trying to amplify. So the mathematical definition of common mode rejection ratio, which is more interesting for us when we're calculating something, is defined as the V output for a differential input, the thing we want to amplify, divided by the V output for a common mode input, the thing we want to get rid of. So it's literally a ratio. So here's an example. Somebody gives us an amplifier that has a closed loop gain of 20 decibels. So this is the amplification of the differential signal. This is the amplification we get for a differential input by definition. It has a common mode rejection ratio of 90 decibels. That's sounding pretty good. That's a big number. And we have a common mode input signal of negative 60 dBV. So that's a voltage value. And we want to know what's the actual output common mode and differential signals. Okay, so what's our, from that we can get our signal to noise ratio, and that will tell us something about how well we can actually discern what the signal is. Okay, well, we have all the information we need to solve the problem. I like to work in voltage ratios more than decibels, so I'm going to start by converting things to voltage ratios, plus my common mode rejection ratio is defined in terms of a voltage ratio, so I feel like that's going to make it easier. So I'm going to start with my differential signal amplification of 20 decibels. So I'm going to express that in a voltage ratio of differential voltage out over in, and I use my 20 decibels, and so I get a value for that. And then I'm going to do the same thing with my common mode rejection ratio, expressing it in terms of its definition, V out differential over V out common, and that's just dropping in this definition right into the decibel expression. So I'm going to turn these decibel numbers into voltage ratio numbers. I'm going to do the same thing with what someone's told me my common mode input is. So I'm going to say negative 60 dBV is the same thing as 1 millivolt, basically, which is pretty hefty if we've got small differential signal. So that's we'd like to see if we can reject that. So we could assume we have an equal differential input applied. That makes it easier for calculation purposes. So we could say that our V out differential over V in differential is equal to 10, because that's what this is with a 20 dB out front. So we can say our V in differential signal is only 1 order of magnitude higher than our common mode signal, our noise. Wow, that's bad. Let's see if we can get rid of some of that noise with our common mode rejection. So now we can invoke our 90 decibel rejection. So we can pop in our V out differential, which we just calculated here, and leave our V out common down here, and solve for V out common, and we get a value of 3.162 times 10 to the minus 7 volts. So this is great. we put in, presumably a small differential signal, and we got a bigger differential signal out, but we put in a 1 millivolt common mode signal, and we got a 10 to the minus 7. We got 3/10 of a microvolt of noise signal out. So we reduced the noise and we increased the signal. This is great. That's what you always want. And as a warning, unfortunately, common mode rejection ratio, like everything else, is frequency dependent, works best in the mid-band, rolls off beyond that. Power supplies have a lot of noise. Ripple, other kinds of rectification-based signals that we really don't want to carry through. And so if we're using a power supply to supply our op amps, which we have to do, some of that's going to come in. And so we can apply the same kind of ratio of differential output signal to noise signal coming in from the power supply, create another ratio similar to common mode rejection ratio, and that's called power supply rejection ratio. So that basically is a ratio of the signal you would want on something that you're supplying with a power supply, or the power supply DC output, if that's considered your signal, over all of the common mode noise sources inherent to the power supply, mainly ripple would be the big one. So almost done. We have just one more paragraph. This is several pages in our Fiori textbook, including one very long-winded example that I'm not going through. When you talk about common mode rejection ratio and getting rid of the common mode signal, which is frequently noise, or defining the power supply rejection ratio, all of that is starting to touch on the concept of noise. And these are signals that you don't want. These are voltage signals or current signals that can be amplified, that obscure your ability to detect the signal that you cared about. Like foreign object and debris, noise is any kind of signal that gets in the way of you detecting the one you wanted. It's everything other than the signal of interest. From an electronic standpoint, there's basically types of noise signals that are frequency independent, ones that are frequency dependent, and that's only important because that gives us a strategy for getting rid of them. Basically understand that unless you can reject them at the front end with your differential amplifier, your noise voltage sources are going to be amplified right along with your signal. And what you're going to care about in every case is not necessarily the total magnitude of your output signal or the gain for your signal or the output or gain for your noise, but the ratio of the two. There's a quantity that we can define as signal to noise, and it's the relative magnitudes of your whatever signal you care about to all the sum total of the signals you don't. And you will see this frequently in all branches of science, but definitely in electronics. Signal to noise is being the quantity you're trying to optimize. Since noise signals are signals, they have the same kind of considerations in terms of bandwidth, gain, everything else, because they are voltage signals. And there are branches of science that use them as data sources, in which case you could argue that they're not noise. But one particular annoying characteristic of electronic noise that's inherent to the operation of components, thermal noise, shot noise, flicker noise, these are all processes that are inherent to the function of a semiconducting device, rectification, etc. Things we really can't get rid of because they're linked to the very processes that our signals are coming from. Those types of noise signals have a bandwidth that is bigger than our signal bandwidth. So our signal gain is going to roll off faster generally as we depart from the mid-band than our noise will, which is kind of a bummer. So I guess that's another advantage to operating in the mid-band region. Your signal to noise will inherently be bigger. And the other rule of thumb with noise is we combine them with the root the square root of the sum of the squares. So if we remember root means squared voltage, we use that same kind of combination when we're adding them all up. You don't just add noise voltage to noise voltage by superposition the way we did offset error. That's not a noise per se, it's an error signal with something we don't want. We were able to add that with straight addition. A noise source we would add by squaring it, squaring the next noise source, squaring the next noise source, summing them together, taking the square root. And that would be the noise that would go into our signal to noise ratio. So for the purposes of this quarter in this course, you might be asked some general questions, qualitative questions about noise on a quiz. We won't be doing any noise specific calculations, although as a warning, if you're going into an internship or a job or doing a specific project in a later class, these are the type of calculations you might get into. But this is it for our op-amp practical limits discussions. This is our second lecture, and so there's only two. Covering the material in Fiore's Op-Amp Text Chapter 5. There's a lot more considerations when you're designing and analyzing real op-amp circuits, but this has hit the main deviations between the ideal behavior that we saw in Chapter 4 and real behavior that is more or less captured on your spec sheet. So read your spec sheet, refer back to Fiore Chapter 5 or these notes to make sure you're deploying those characteristics properly, know what they are, and then it gives you some strategies for getting the most out of your circuit and selecting the right components. So if you are taking this course in winter 2020, this is the final recorded lecture, and this is the final topic for our ENET 140 op-amps course. We will have a quiz that is open now and is due midweek next week, and then our exam, which covers this material, just the practical limits Fiore Chapter 5, at the end of next week, due on Friday. And then that will be it for the course, and we will be looking ahead towards digital circuits and digital logic for the next 6-week period. And see you then for that.